All right, hey, good afternoon, everybody. Thanks for joining me for the early show. Your headliners will be on later tonight, and don't forget to tip your waitresses. What I'm gonna do is talk a little bit about a trend that's going on right now that really spans space and artificial intelligence. It's called global monitoring. And what I'm gonna talk about today is how we do global monitoring, how that's evolving, and how eventually it's gonna be driven by artificially intelligent machines collecting data around the world. So what I'm gonna do is talk about a number of different topics. So let me start first with a little bit about myself. My name is Scott Herman, and I'm the CEO of Cognitive Space. And we bring artificial intelligence to the world of satellite operations. And I'll talk about that a little bit at the end of the brief. But what I want to do is kind of set the stage around this topic of global monitoring. Real world showcase. I'm going to show you some real world examples of how global monitoring is done from space. I'm going to talk a little bit about how remote sensing satellites work and what are some of the changes that are going on in this world of satellite remote sensing. I'm going to talk about how artificial intelligence is playing a role, not only in terms of dealing with the data produced from satellites, but how do we actually use artificial intelligence to drive the satellites themselves? So let's get started. Well, first of all, global monitoring with satellites. You know, we've been taking satellite imagery for more than 50 years now. And the idea of monitoring change over time is not a new concept in of itself. In fact, you can see in this example, it should look familiar. This is right here in City Center in Las Vegas. We're seeing a recent picture of the hotel and also a year ago or a couple years ago when it was being built out. So this idea of monitoring change isn't new. So when I say global monitoring, as a new thing, as a new trend, what am I really doing? Well, let's define that a little bit. The first thing is monitoring is about specific activities and facilities. You're going after them on purpose, right? It's not just a matter of mapping the Earth and looking back retrospectively or forensically to say what happened over time. This is about, I want to watch that particular facility or that particular activity. There's a specific mission. It's tend to be dominated by national security, but we're seeing that change into economic monitoring, environmental monitoring. I'll show you some examples of that. It's about now. This is really important. This is about using satellites to see what's going on around the world today, not 3 months ago, not a year from ago. This is about what's happening now. Currency and perishability of the data is really important. It's about often. It's being able to collect at a cadence that allows you to build up observations and determine what's called pattern of life. How does this facility actually operate? When is the surge times? When is it closed? When has there been a crisis? How do you detect anomalies in that pattern of life? So let's start first. I'm going to run quickly through a number of real-world scenarios. So 150 slides, 50 minutes. Everybody ready? Let's do it. All right. So the first thing I want to do is talk about activity monitoring. And activity monitoring is an activity that may span several different locations or a larger area. In this case, what we're looking at is a set of recent fortifications in Libya. And this particular observation was made by a synthetic aperture radar satellite from a company called Capella. And I wanted to start with this one because usually when people think about satellite remote sensing, they think images. They think of visible light color images like you see on Google Maps or Apple Maps. But there's a lot of different phenomenology that you can apply to this problem. Airfields are a common topic for facility and activity monitoring. Here's an example from Black Sky where we're monitoring a particular military airfield and watching activities there. One of the things that's interesting about global monitoring is that it can happen at all times of the day, right? We want to understand from a pattern of life perspective what's happening at a facility 24/7. So that means collecting at night, it means collecting through clouds, it means collecting at a very high cadence, a very high time series of observation. Again, you know, kind of the national security perspective has really dominated global monitoring. We're seeing an example from a company called Satellogic, where we're looking at a nuclear facility in China. Here's another example in China. This one's from Airbus, the Pleiades Constellation. And what you're seeing is a launch facility, and then a few days later, something bad has happened. If you look on the right-hand side, something blew up on that pad. Well, if you were only monitoring that every few months or even every few years, you wouldn't necessarily catch that anomaly. This is an example of anomaly that's been caught because we're watching this facility at a higher cadence. A hot topic right now, you're probably seeing this in the news, is the launch of the recent third Chinese aircraft carrier. So several different companies, several different satellite constellations have been watching as this aircraft carrier has been built in the dry dock. And you see an example here from a few weeks ago. This carrier is important not only because of the national security implications of the power projection capability of this type of ship, but also notice it's the first one that the Chinese have built to use catapults. And you can see this kind of covered up there in this picture. Now let's go just a few days ago. The ship is getting ready to go. They've flooded the dry dock. They've hung the parade pennants, so they're getting ready to like smash the champagne and launch this thing. So the point of this is the level of observation cadence, the level of resolution, and the time of day that we're collecting against. Time of day is really important. Look at this example. This is a radar shot. In this case, this is coming from a constellation called ICE-I. And what they've done is notice the time over target. When was this collected? 3:14 in the morning local time. In other words, pitch black. So by using radar, we're able to see activities that are happening at night or beneath the clouds. And what you can see in here, if you look at that pier at the far northern end, there's another one of the Chinese aircraft carriers. This is a different one, but you can see that we're kind of monitoring it 24/7 using a range of different satellite types. This idea of cadence is really important. How do you build a time series? And then once you have a time series, how do you determine anomalies in that time series? What we're looking at here is a great example from Black Sky, where they're monitoring the border crossing between Ukraine and Poland, and then actually collecting every few hours, and then doing analytics against the number of buses that are backed up at the border. And we can see they start growing as more and more people were flowing out of Ukraine. So that's pretty interesting. If you look at the times are like in the evening, first thing in the morning, right? We're doing dawn to dusk collection, even in visible light. Here's another example with a geopolitical perspective. They're building a new dam on the Nile River. And there's been this debate about if you dam up the river, what happens to everybody downstream, especially when you want to fill the reservoir. So what you're looking at here is an analytic example from a company called URSA using radar data from the European Space Agency's Sentinel mission. And what you're seeing is the day they basically close the dam and start filling it, it's only 2 weeks before they have a decent sized reservoir there. So what are the implications to that in terms of that volume of water downstream? Now, I've shown you a lot of national security and geopolitical, but one of the trends that's happening right now is a move to have this kind of almost defense-related visibility, persistence, start applying toward other missions like environmental and economic. So here's an example of environmental monitoring, and this is about wildlife poaching. So we're not only seeing things like elephants from space, those little blobs are actual elephants that you can count using analytics, but also in the upper right-hand side, observing the Earth happens across a number of different spectrum. It's not just visible light, it's not just radar, multispectral, hyperspectral, it's radio frequency as well. And what you're seeing in that example in the upper right is a company called Hawkeye 360 monitoring for radio frequencies in areas where there shouldn't be any. So if there's poachers using cell phones or walkie-talkies, that could be detected and they can point the anti-poaching groups to that part of the reserve. Environmental monitoring for agriculture has happened for a long time. Trends over seasons, crop forecasting. What's different now is this ability to do it at a much, much higher cadence and at a level of precision that allows you to do individual crop health and actually tell the farmer so he can make some reactions to that during the growing season. Wildfires is another example. Climate change, this is an ice cap melting in Greenland, I believe. Environmental monitoring, things like mining operations. This is actually from Planet, shot in infrared, so there's lots of different ways to look at what's going on. Economic monitoring is a really hot trend right now, particularly around Wall Street and the focus on hedge fund trading, anomalies make money, and also ESG, right? Kind of environmental governance for stock portfolios. The other thing that's really been trending right now is supply chain. And we've all heard a lot about supply chain in the last year. In this case, we're looking at Long Beach, California. This is the container terminal. And what we're looking at is all of the ships out at sea waiting their turn to get in. This is a backlog. This is a throughput issue. And by measuring from space and taking observations at a very high cadence, you can determine things like the throughput through this particular facility. In fact, here's an example where we're taking 7 shots in 7 hours. This is from Black Sky. And what they've done is they've run an analytic against that to do things like determining throughput, identifying specific ships that we're seeing in the images. So you kind of get a sense of this level of persistence. This is not location-based services and Google Maps and Apple Maps, which is what most people are familiar with. for satellite imagery. This is about staring at things right now and determining what's happening right now. Here's another container port example. If you look really carefully in the center, you can see there's a collapsed crane there, right? So this image was taken just after that crane collapsed. I mentioned radio frequency collection. One of the things we're able to do now as an industry with suppliers like Hawkeye 360 and Spire and Cleos is get at radio frequency information and then use that to monitor what are called bad actors. And this is a bad actor example. This is the economic exclusion zone around the Galapagos Islands, and that swarm you see down at the bottom is the Chinese fishing fleet, fishing right up to the edge of the EEZ, and then occasionally skirting across to sneak in. And so this is an example of how you try to find that when it happens for monitoring. Everybody cares about gas prices right now. One of the things we can do, and this is a radar shot, again from Capella, and what they're doing is they're monitoring storage tank farms, petroleum storage tank farms. Those lids on top of the storage tanks float, they move up and down. And because of that, they present a radar shadow that can be used for volumetric measurement of how much is actually in the tanks. You guys probably remember this, the Ever Given that got stuck in the Suez Canal. So here's an image that was taken of the ship. This thing was shot by probably 20 different companies, all collecting information about the Suez. Here's another example, nighttime radar of that same facility. And then you can also see those blobs to the north are the dredging and tugboats that are kind of there trying to push and move things around. One of the trends right now that's happening is this ability for global monitoring data to be used in the press, right? Not national security, not Wall Street, but actually in the press to tell stories. You probably have seen a lot recently about Ukraine and some of the satellite imagery that's being used to support the storytelling, the understanding of what's been going on there. Here's an example where that one image of the Evergreen wound up being distributed worldwide. You can see a whole range of international papers and websites picking up on that image. This idea of global monitoring the media is something that is really catching fire right now. Part of that is because of the availability of data. There's so many more companies and organizations flying satellites now, but also the capability to take the shot, interpret the results, turn it around very, very quickly. It's not forensic, weeks, months, years potentially. This is about hours to minutes in terms of understanding what's going on. So let's switch gears a little bit and let's talk a little bit about how remote sensing satellites work. Because I think that's kind of important. I can't talk about big mega constellations and AI-driven collection if you don't understand the basic problem. So these satellites are basically sensors. They're flying sensors. And these sensors are pointing down at the Earth and making measurements, making observations. They may be making those observations in visible light. They may be making them in hyperspectral or multispectral. They may be using radar, not only synthetic aperture radar, but like ground penetrating radar to find things under the ground. It could be radio frequency collection. This particular example you see on the screen, this is a satellite that's basically using radar to punch through the clouds and kind of paint the Earth underneath. So what I want to do is walk you through an animation. This is a typical remote sensing satellite. Many of these satellites are what are called agile, meaning they can move around in 3 axes along their orbit path. And what that means is they can point, okay? So just like taking a picture on your camera on your phone, you point at a target. And what you'll see in this example is this satellite is working off a target deck, a set of orders from customers that say, I want pictures of all those points that you see on the ground. So it's picking them off. That yellow beam is it downlinking the data, in this case to a facility in the Washington, D.C. area, to get that imagery off the bird as fast as it's taken. You'll notice about halfway up on the satellite, there's a couple kind of conical shaped objects. Those are actually cameras that look out the back way. They're called star trackers. And they look at the star field, the black star field behind the satellite, and they align the satellite against that star field. And that's how the satellite can do such precise pointing as it moves around its axes. Some of these satellites have the ability to collect pretty large areas. You'll see this satellite is now collecting against deep water oil facilities, the big offshore derricks and things like that in the Gulf of Mexico. So that was one satellite operating. But what's different right now, what's trending right now, is tying several satellites together, working together in a common constellation. So like you have a flock of birds or a fleet of ships, we call it a constellation of satellites. So the idea is get that constellation bigger and bigger. The more satellites you have working together, the more frequent your collection, the more of the world you can capture, the more capacity you have for your customers, and you keep growing and growing and growing. These deployments take time, so often you'll start with a few satellites and then launch a few more and launch a few more, so your capability stair steps up higher and higher. I may have 3 satellites this year, I'm gonna have 300 satellites 5 years from now, right? That's kind of the idea. And then you go convince investors and hopefully they throw money at you. Eventually, all these constellations from different organizations, from different companies, are all flying in the same space, literally space. And many of them fly in what's called a low Earth orbit. And so this is an example of just how crowded low Earth orbit can be. And this is only gonna really, really increase as more and more companies and organizations start flying these swarms of satellites, what are sometimes called mega constellations. GPS is probably the best known one, but Starlink is coming up fast. But in the remote sensing world, there's a number of different companies that are launching satellites for remote sensing. So let's switch gears a little bit and talk about some of the trends that are happening right now in new space. And what I mean by new space is basically the emerging capabilities coming out of the commercial world that can be applied towards space. This isn't the world of big government and big defense and aerospace anymore. This is about small companies. This is about venture-backed companies. This is about very fast innovation. Let's talk about some of the trends that are happening in the new space community that impact this mission of global monitoring. Probably the first one is this move towards small satellites. Historically, for almost 50 years, we've been building Battlestar Galacticas, right? These are billion-dollar satellite programs. They take 7 to 15 years of engineering. Tends to be the world of the US government and some other major power players, and working with the massive aerospace contractors, Lockheed, Boeing, et cetera. You can see there on the left, right, we're talking about satellites the size of school buses, massive clean rooms, people in bunny suits, a very expensive and slow way of building satellites. What we're seeing now, though, is this move to small satellites, something that can be built on a college lab bench. And this has really been driven around things like the use of commercial components, the use of standardized components, and the ability to build stuff in a throwaway fashion. It's almost like agile software development for hardware. It doesn't have to last 10 years. It can last 2 years, and I'll throw another one up there, right? That's the concept. In fact, in the lower right, that rack you can see, those are actually Planet Dove satellites. These are cube satellites, and literally it's just a rack with a whole bunch of them on them waiting to get shipped off to the rocket so they can get put up into space. Which is the next trend that's happening right now. There's a very important trend right now around cheaper and easier access to space. There's been a proliferation of new commercial providers. SpaceX, of course, is the most famous one, but there's 20 more in the wings behind SpaceX. And so what we're seeing is an ecosystem develop where, just like getting a seat on an airline or paying freight through UPS, you can basically say, I have a satellite, or I have a family of satellites, I have a constellation, I need them in these orbital configurations. What kind of ride can you put me on? And you get pricing for that, and you work with these different suppliers. Closely related to this is another trend called ride sharing or piggybacking. And that's the idea of, I don't have to buy an entire rocket for my own small satellite. My small satellite may have only cost me $5 million to build. I can't spend $100 million on a launch. So you piggyback. You say, let someone else pay the freight. I'll pay a little fraction of it. I just want a seat. I don't want the entire airplane. And what happens is you can go up, and these new missions around ride sharing actually launch dozens of satellites at the same time. This particular one, 87 satellites were deployed in one mission. And what you see there in the center, this is from Spaceflight Industries. It's called a Sherpa. And a Sherpa basically packs in a bunch of satellites, ferries them up to orbit, and then shoots all the satellites off at the appropriate time. It's almost like a bus stop, right? Oop, your stop is here. I'm letting you go, establish yourself in orbit, and rinse and repeat. Another really important trend that's happening in new space right now is this idea of multi-phenomenology sensors. I talked a little bit about visible light versus radar and hyperspectral. One of the things that's happening, because satellites have gotten cheaper, because it's easier to get to space, because there's this need from global monitoring, it means that you can now build more exotic phenomenology and get it up into space and see if you've got a business or not. This leads to a trend where we go from larger constellations with inclined orbits, right? Lots of different kind of orbits. On the left is kind of the way it used to be. You would put up 1 or 2 satellites, you'd put them into a standard, what's called a sun-sync polar orbit. Now you put them up in all kinds of different orbits, right? You'd want to disperse so you can have that 24/7 collection or that dawn to dusk collection if you're visible light. You want to have capacity to manage as many customer things as possible. So for example, what we're looking at here, each of those little polygons is a picture. It's an observation that was taken, and each color represents a different supplier. So it kind of gives you a sense of what happens as you start collecting again and again and again and again many times a day. And that allows you to build out what are called high cadence time series, or sometimes called stacks, like a stack of pancakes. And you can see on the left there, the idea is I've got several different observations. They may be from different companies or different constellations. They may even be different phenomenology. But by having that time series stack, I can now determine pattern of life and find anomalies in that pattern of life. And what that lets me do is bring in another trend, which is the use of artificial intelligence for the analytics themselves. In this case, what we're looking at is computer vision models that are pulling data out of those images, establishing counts and trends, and looking for patterns of activity. This can take a lot of different forms. In the upper left, you've got rooftop analysis for solar panels. On the right, you've got the identification of oil storage facilities. In the lower left, we're identifying particular kind of aircraft. In this example, we're pulling building footprints and classifying the building types, all without a human in the loop. This is all artificial intelligence and computer vision. The final trend I want to talk about is this idea that this is all commercial. This is the world of startups. It's the world of venture-backed and private equity-backed companies. This is about subscription services. This isn't about these big, giant NASA-like space missions that we've had in the past. And what you're seeing here is just a smattering of some of the companies that are playing in this realm right now. You have the satellite operators. You have analytics companies. You've got a variety of different providers like IoT versus Earth observation. You've got space-based relay, which is a way of getting that data down to the Earth really quickly. So if we're going to have all these satellites, and we're talking about constellations that are large, this new space concept has a lot of promise, but it also has the potential for real chaos, confusion, and contention. We're talking about thousands of satellites, tens of thousands of sites to monitor worldwide, dozens of revisits per day, very complex technical and orbital constraints that you have to kind of solve for, dynamic and competing customer demands, data-starved analytic applications. There's a lot of cool analytics out there. They just can't get the data. You can't exploit what you don't get, right? So this idea of analytics-driven collection is really hot right now. You know, what we really need is an autonomous brain that lets us orchestrate all of these satellites. So did I mention I work for Cognitive Space? Space is hard, we make it easier. Let me tell you a little bit about what we're doing in this realm of AI-driven orchestration. So what Cognitive Space does is we apply artificial intelligence to kind of revolutionize satellite operations, particularly in the realm of mission management, collection planning and orchestration, future capacity forecasting. It's not only about optimizing your current satellites, it's about thinking about how your constellation is going to operate over the coming years. How do I coordinate all my comms links, both Earth-based and space-based communication relay? And then how do I deal with the blocking and tackling of order management? How do I get money and requests from my customers? So things like customer and partner portals and APIs, et cetera, all running on Amazon, of course. So there's a real opportunity here, and where Cognitive Space is really focused is trying to offset this particular pain point in our industry, which is, yes, I want to put up a satellite constellation, but if I'm thinking about how I build out my ground architecture and my ERP-like capabilities to monetize my sensors, I'm looking at a multi-year adventure in pain, right? I've got cost risks, technical risks, schedule risks to deal with. Usually it's build it myself, and how do I find the team to do that? What Cognitive Space is doing is really providing a blueprint and an operational capability to optimize and operationalize your satellite constellation. So we kind of do this through a set of new tools for new space, and they kind of fall into three categories. The first is this idea of optimizing. How do you optimize your current operations? How do you apply AI to solve for the best revenue performance, or the best capacity performance, or the best monitoring and revisit performance? How do I prioritize my customers? And how do I manage a constellation of 50, 100, 1,000 satellites without having armies and armies of people? Instead, we want to do it dynamically and autonomously using this lights-off brain that's kind of figuring everything out. Second area we focus on is forecasting. And forecasting is the idea of what does your future constellation need to do? How do you kind of war game and figure out what kind of constellation do I need? How do I convince my investors? How do I convince my early customers that what we're building is really going to exist and service their needs? And how do you do that at a high fidelity modeling and simulation environment? The third thing we focus on is orchestration, and this is where we do a lot of work with the US government, where they may not necessarily be flying their own satellites, but they want to take advantage of all this new space capability that's coming online. So they need to figure out how to orchestrate. They need to figure out how to do things across constellations and reconcile differences between suppliers and phenomenology, and is the data analytics ready, and all of these other issues. So most of the work we do today with the US government and the allies is in that orchestration category. So what I'm going to do is I'm going to spend a few minutes and walk you through a few demos to kind of give you a sense of exactly what we're doing. And these are all workloads that run within our Amazon environment. So the first thing I want to do is talk about future constellation modeling. How do we war game? How do we look ahead? What we're looking at here is, and this is straight out of our user experience. So these are just screen captures of the cognitive space application. So what we're looking at here is this is a constellation that will eventually grow to probably 90 to 100 satellites over the next few years, collecting synthetic aperture radar. And what we're doing is we're trying out different types of orbits. You'll see a number of polar orbits, a number of inclined orbits to give you better equatorial coverage and better coverage throughout the day. And we can try out different things, but it's not just orbitology. This isn't simply a satellite toolkit on steroids. What we're looking at is revenue optimization, performance optimization against the things that these companies' customers want them to do. Don't forget, there's a reason we're going to space, and rockets are cool and satellites are cool, but the mission of what we're doing and how we collect that data and analyze and exploit it to better understand the Earth is the mission. So what you'll see on the far right side there, you'll notice a set of targets in the South China Sea, all those little yellow dots. Let's go take a closer look. We're going to take a few minutes in the life of one of these satellites, Predisar 21, as it comes on mission over this area. So what you'll see happen is it flies up from the south. That blue dashed line is the artificial intelligence engine nominating targets. It's basically saying, hey, satellite, these are the ones you should collect on for the best optimization bias. And so what you'll see is as it flies over, the blue dashed line is the AI, the green is the satellite reaction. How long does it take to maneuver and set up the shot? And then you'll see it collecting on different targets. And you'll see that it skipped a whole bunch of them. It went after those higher value targets out there in the middle of the South China Sea. And that's because those are really high priority targets. Mischief Reef, Subi Reef, Fiery Cross Reef. Those are Chinese military installations out in the middle of the South China Sea that are kind of challenging some of the shipping lanes out there. So the AI makes decisions like, I can get 3 really high priority targets if I skip these others. The other thing you'll see, it's repeating now, just as it leaves the area, it reaches back and grabs a commercial target, a deep pit mining operation in the southern Philippines, because it's able to optimize for that and say, I can still get that within the product constraints. Well, this gets really complicated when you start talking about a lot of satellites. And here's an example about midway through the build out of the constellation. Remember, this is going to take several years to get built out. But you have today's capability, midterm capabilities, final capabilities. What we're looking at here is collection against a set of Iranian targets by the swarm. And the AI is driving the collection decisions and providing a very detailed set of instructions. These satellites are basically robots, right? They're intelligent machines that you tell what to do. Slew over this way, take this observation. Now slew over that way, take that observation. Downlink your data, right? We give it a very detailed program, essentially, of what to do. So let's go take a closer look at what's happening here. These are synthetic aperture radar satellites, so they tend to be side-looking, right? SAR satellites don't look down, they look to the side. And that's where you get these butterfly wings that you're seeing in the simulation. That's the field of regard for those satellites. Where can they actually collect? And you'll see as they work those targets, the satellites are kind of working together. They all know about each other, and they're doing things like, you take that pass, I'm going to take this one, and I need to build up my revisit, my number of expected collects per day, over each of these targets. So that's really key, right? We're swarming the satellites against a common set of targets for collection. The other thing you're seeing happening is we have 2 different customers in the region, right? We've got the United States, they're at Bahrain, that's the 5th Fleet. So you'll see that some of the data is being downlinked to them as soon as it's taken. So this idea of latency, how fast can I get the imagery? But we have another customer there. This is a UAE customer This is the folks just outside of Abu Dhabi at Falcon. And so the system is determining for this order, I'm going to take this shot and downlink it to this customer and keep them all straight so that they don't step on each other. So how do we do this? What technique are we using? We have an AI engine we call our cognition engine. And that's how we do our orchestration. And it's really based on a technique, a machine learning technique called reinforcement learning. Reinforcement learning is a technique that's really good at finding solutions out of a whole set of possible solutions, right? There is no one right answer. There could be dozens, hundreds, thousands of possible answers. It's kind of the traveling salesman problem on steroids, right? Fleet management or like getting your airline tickets, right? How do you get routed around? What we do is we actually take a page from the gaming industry where these GPU-enabled reinforcement learning engines are now beating the best human players at things like Go or StarCraft. Our game board is actually this complex mix of hundreds of satellites, tens of thousands of ground targets, very complex orbitology, technical constraints of the satellite. What can the satellite do or not do? How do you protect the satellite? What is it capable of doing? What's the weather, both on the ground and in space? How do I get my data to the ground? How do I task the satellite? How do I tell it what to do? So this sea of constraints is made up of tens of thousands of variables. The reinforcement learning is constantly solving to try and find the optimal solution. And it can optimize on different, what we call biases. So am I optimizing for pure revenue? Like get me the dollars, it's end of the quarter. Am I optimizing for capacity? Collect as much stuff as you can collect. Am I optimizing for revisit? Look, I've got 500 facilities. They all have to be collected 5 times a day. If I've only collected it 4 times and I've failed now twice because of clouds or other issues, that 5th collect starts dynamically moving its way up the stack and becoming much more important in the schedule and reschedule and reschedule and reschedule. There's really 2 pieces of IP that we're bringing to bear. One is how do you apply reinforcement learning to this problem? The second is a DevOps problem, right? How do we use our Amazon-based architecture to be able to run at this level of scale and complexity within the time frame of just a few minutes? Right, this isn't an AI problem where we go let it run for 24 hours and it solves for a solution. It's got to be able to happen very, very quickly. So things like scalable microservices and our AI pipeline all becomes an important part of the solution as well. And the payoff here is that traditionally flying satellites have been flown in kind of onesie-twosies. And it's either been done through manual adjudication, and I kid you not, there are satellite operators that sit there with a whiteboard and a spreadsheet to try to figure this out every day. Or they use what are called heuristic rules, expert rules. You know, if this, then that, or if this, then that, right? You try to encapsulate it. Heuristics can do a good job, but they're very brittle, right? And if you're constantly building a constellation where you're adding more satellites, adding more satellites, adding more satellites, whoop, this satellite needs to be pulled out because it croaked, right? It's got an anomaly on it. I've got a whole different set of customer perspectives. I just added a whole new customer that bumps the entire prioritization of what I'm trying to collect. You need to be able to adapt to that very quickly. And our AI techniques not only give you better yield, but they're very adaptable and they're not as brittle. So what you're seeing in this particular simulation, on the left-hand side is a traditional heuristic algorithm working against this set of targets. On the right is our AI-based system. And if you can tell, if you watch this, you can see that the one on the right is picking off many more targets than the one on the left is, because it can make decisions about all these trade-offs in near real time, right? And so what you get is on the left side, we collected 25. And on the right side, we collected 113 targets in that particular pass. So those are the kind of the magnitude of difference we're seeing. Now, the satellites have to be able to support that, and there's lots of ways to tune heuristics, so take it with a grain of salt. But we're seeing really good results in terms of this AI model for doing performance optimization. So one of the things we've been doing recently is we've actually been looking at a particular problem, and this is Chinese investment in precious metals mining and extraction in Latin America, particularly along the Andean Altiplano. Think lithium, right? And so what we wanted to do is we wanted to say, look, there's 75 facilities. We want to see how these future constellations are going to be able to collect against that, and what is going to be the benefit for government users, for commercial users, in having this much data. It's not just a volumetric tidal wave. Right? It actually changes your tradecraft, your training, your tooling, even your procurement models, because there's now 40 different suppliers of this data. So what you're seeing in this example is, again, the blue dashed line is the AI making nominations, and the green is the satellite reacting and making those collects. So you can see we're picking off a bunch of targets there. What we can do is kind of fast forward, and we say, here's all these facilities. I need to collect them 5 times a day. How many passes is that going to take? And this is kind of that high fidelity modeling and simulation. I'm fast forwarding through several passes, and you'll see them turning green as the SLA, the service level agreement, is met for those particular facilities. So happy customers pay better money. So that's kind of what's happening there. And then we think about how do we use different kinds of satellites from different constellations, from different providers. How do we use them in unison? How do we build a virtual constellation? So in this case, we're still looking at those same set of economic targets in Latin America, but I'm flying 3 different constellations from 3 different companies against it to try to maximize my yield by using them together. So you see the radar satellite, there's a hyperspectral satellite, there's also a very low Earth orbiting electro-optical satellite. And then you can see the metrics in terms of things like total collection, mean time to access, level of revisit, facility by facility. And you can compare and contrast these different models to find the right one. Another thing we're really focused on right now is what's called space-based relay. And this is how do you get tasking to your satellites and how quickly can you get the data back down to the ground. So one of the dirty little secrets about satellite imagery is that basically people think the satellites zip around like a space battle. They don't. They're in a consistent orbit and they wait for the Earth to pass by underneath. And if the ground station that you're going to dump your data to is in another part of the world, you kind of got to wait until you fly over it, establish a connection, and then dump your data. Space-based relay is a way to just short-circuit that entire thing. Put comms relay satellites in space at geosynchronous orbit like this, or at low Earth orbit, or MEO. There's many different configurations. There's a lot of different companies playing in this world. Hedron, SpaceLink, Skyloom, Warp Space are some examples if you've run into those companies. In this case, we have a satellite flying close to the Earth. We're doing collection, but it's actually backhauling its data using space-based relay to the other side of the planet as that imagery is taken. Very powerful concept. So a couple more slides to wrap up, and I'll take some questions, but let me talk a little bit about how do you get your hands on this kind of capability. Well, I mentioned the forecast capability, this modeling and sim capability. It's something we call sentient forecast. And it's a way to look into the future of your constellation. And basically what we do is we take constellation design. What are the different types of satellites in the constellation? What are the versioning and capabilities of those? You can have many different types of satellites. What are the anomalies in that one? Every satellite, even though you build hundreds of them, may be a special snowflake. This one has this anomaly, this one's flying at this orbit, this one burned out a reaction wheel and doesn't turn as fast. All those kind of things can play in. And then we build that up into a constellation design. We also take the collection targets, and the way to think of collection targets is these are customer orders. All right, this is what customers want you to collect so you can feed this analytics ecosystem. And then this runs into our sentient engine in the center. We have different scenario configs. Am I modeling 3 days or am I modeling 3 years? Am I trying to do this for revenue bias or am I doing this for capacity bias? And then what comes out is a whole set of simulation metrics and results, as well as a very rich 3D visualization, which lets you kind of war game and play around. So if you're in the satellite business, and this sounds intriguing to you, we're actually offering this as an enterprise SaaS capability that scales as you grow. So if you're a startup, you're out trying to get your funding, you're trying to get to your first launch, your pre-revenue, we have a whole set of capabilities at a low price that's mostly focused around this future forecasting and getting ready for your Pathfinder launches. If you're now flying and taking customer revenue and you've got your first operational satellites up, we have a growth mode for that early constellation. And then when you're really doing it, right, you've got competing customer demands, you've got competing comms, communication coordination to go on, you're flying, dozens of satellites. We have an enterprise class product as well. And there's a different feature set for each one and a different price point. So who are we really focused on? What are our go-to-market segments as we build cognitive space? Well, probably the most important one is these new space constellations themselves, the satellite operators that are building out these, eventually mega constellations and swarm-based remote sensing constellations. We also work a lot with US defense and intelligence and international governments who may not only be trying to take advantage of commercial capability, but maybe flying their own satellites as well. I talk a lot about commercial, but this is very applicable to government missions as well. You may not be optimizing for revenue, you may be optimizing for a lot of other things. And then in terms of partners, a lot of the new space infrastructure companies, this obviously becomes a value-added service that they can bring along with some of the things that they're doing. And of course, traditional aerospace and defense companies, kind of helping the dinosaurs evolve and adapt and get an innovation injection. So I'll wrap up real quick and then we'll take some questions. But probably the biggest takeaway is, so this is all cool, Scott, but why should I care about cognitive space? And I would say that there's probably 5 things to think about in your conversations when you go back home and where cognitive space could play. The first is this idea of AI-driven satellite collection and what can that actually do in terms of mission management and collection planning. The second is our focus on swarm operations and flying a constellation as a holistic whole and doing that in a lights-off manner where you still have very dynamic tasking and ordering parameters. This leverage of all of these new commercial space capabilities, we're talking and working with a huge part of the ecosystem, and we can help figure out how do you take advantage of all of this emerging capability that's coming online today and coming online over the coming years. We also are a really good shop for kind of seeing the future. So ConOps development, concept of operations development, rapid prototyping. This is a lot of where the US government kind of uses us. Agencies like Space Force, the Space Development Agency, the Air Force Research Lab, National Geospatial Intelligence Agency, NRO, they're all working with us on this idea of how do we kind of figure out where we want to go in the future? How do we establish some of these big systems engineering and architecture goals? And then finally, we have a pretty deep dual use legacy. And dual use means national security, but coming at it from a commercial perspective. And I mentioned our focus on national security, environmental, and economic monitoring, helping new commercial entities figure out how to play in new space, but also having a deep understanding of customer number one, the one with the deepest pockets, the one with the deepest legacy in this area, which is kind of the defense and intelligence community. So how about that? I made it all the way through with some time to spare for Q&A. So if there's any questions, I'd be happy to take those. And you have to help me out because I can't quite see with the lights. Yes?
So many satellites in orbit, I'm wondering, are you also managing like when they go bad or get old, making sure they don't hit a house on the way down?
Yeah, so the question is, that's a lot of stuff up in space. And what is the management of satellites in terms of collision or retirement and what's really going on there? So a lot of the optimization we're doing, we will take feeds from other companies or organizations that are doing what's called conjunction analysis. In other words, what are the potential collisions and how to those? We aren't doing station keeping in particular. We take station keeping into account in terms of figuring out what our collection process is. The question of how much stuff is going up is a real one, and there's a lot of discussion around space debris and space traffic management. It starts with a concept called space situational awareness or space domain awareness. You can't manage what you don't know is out there. The reality is that while there are some licensing constraints on satellites, in general, it's the Wild West out there, right? And a lot of stuff is going up. The advantage to low Earth orbit is anything in low Earth orbit eventually decays and falls back to Earth. So there is an eventual cleanup, self-cleanup, but how long does it take and what happens if it bounces into something in the meantime? Space is a really big place. There's a lot of space out there, so to speak. No pun intended, or maybe intended. But things tend to travel at Mach 25. So when something hits something, it's really bad news, even though it's mostly empty space out there. The other thing is satellites tend to fly in clusters, right? They tend to fly in common areas. They're not equally distributed around the Earth. I often joke that Earth observation is like watching a NASCAR race because you sit in the stands and it's quiet for 2 minutes and suddenly 50 cars come rushing by. So there are tight clusters. So when you think about things like, how do you retire your satellites and what's happening in terms of collision, that's all something that factors into that. As you get into the higher orbits, mid-Earth or geosync or even cislunar, that stuff's staying out there forever. So it becomes a different discussion about, do you propulse it out to a graveyard orbit? Can you bring it back down to Earth safely? And what happens if you lose comms with your satellite, right? There is no recovery without it. It's a huge, huge topic. It's not an area that cognitive space specifically focuses on, other than it's one of those sea of constraints inputs into the larger solution that we're generating. Other questions? Yes? Yeah, so the question is, when you're looking at targets, how many orbits ahead do you look or plan? Some of that depends on the business model of the company that we're working with, but in general, we're looking ahead anywhere from probably 3 days to 14 days for an operational scenario. For the modeling and sim of the future, it can be months, years, it can go really far out. One of the things that we do that's kind of unique, a lot of times your modeling and sim group is very different than your ops group, and therefore they use very different software and very different algorithms, and then the poor business development and salespeople sell something that the ops side can't actually support. We're actually using the same core engine. So that means that what we're doing in terms of future forecasting and support to business development activities is the same core software that's going to be used to operate the satellites. But generally we're looking out, days. Now the calculation of rescheduling can happen in minutes. So changes can happen up till you task the satellite itself, right? So it's not something where it's like you bake it 3 days in advance and you wait. You can constantly reschedule. And so if you have a crisis ad hoc that comes in, something just blew up around the world and I now need to take that shot, the system will recalculate and regenerate the schedules. Yes? Yeah, so the question is weather forecasting. And certainly for Earth observation satellites, if you're not shooting radar, which tends to ignore clouds and nighttime, things like weather really matters, right? And so we take in near real-time weather feeds and use that to make adjustments. If it's going to be cloud covered, right, then there's no reason to take those shots. We can save that capacity for somewhere else. We also look at weather not only in terms of near real-time weather, but in future forecasting. So things like seasonal and regional weather trends actually helps us tune the studies more correctly for what a potential yield might be in that area. Other questions? Yes.
What would you say are the open challenges in AI, computer vision, and multimodal machine learning research with the most potential for impact? Like, what is hard right now that we can't solve that if we could would have major applications?
Well, I will tell you a couple of my pet issues, right? And you can take them for whatever they're worth. But because I do a lot of work in the national security arena, the things we're looking for with computer vision don't have giant sample sets. And so algorithms that can work with very small sample sets or synthetics that can help us train in a way that we don't get really good at finding synthetics, right? If you guys have worked in computer vision, you know that's actually an issue around synthetics. I'll give you a perfect example, right? If I'm training my system to find radio towers, and the system knows from the sample set that all my radio towers have shadows, the shadow becomes part of the radio tower-ness of the object. And then you have a cloudy day, and it doesn't find the radio towers because the sample set wasn't reflected correctly. Certainly in the defense and intelligence world, you're looking for things that you don't commonly see. Have the Russians deployed T-90s to Ukraine? Right? That's a real world question. Well, where's your sample set to train your computer vision models to find T-90s in the wild? So I think that's a really important issue in terms of the use of computer vision for satellite imagery. You can't just go hit stock photo libraries and find 10,000, 50,000 pictures of cats, right? So that becomes an important issue. In terms of some of the reinforcement learning work that we're doing, I think our biggest challenge is how do you continue to run at a scale, at an operational tempo for mission operations as you get into hundreds of satellites and tens of thousands of ground targets? One of our big challenges is not only getting the algorithms right, but getting the DevOps infrastructure right, the scalable architecture infrastructure right, which is why I'm here at the AWS show. Other questions? All right. I'll be around all week if you want to follow up and talk to me directly. Happy to do that. Thanks for your time today. I really appreciate it.